Okay, let me see if I can download a video. How's everybody doing? I can see the excitement. Okay. Let's see if this works. Oh, where's my space? Okay. So Dylan and Samantha, I want to know if you can see. You can see it right now. You cannot? Okay, give me a minute. Okay. Okay. Yes, you can see the guy standing on the handstand. Okay. Okay, so one of the things that we've been talking about for the last couple of days, well, just yesterday, is this idea of equilibrium and the idea of center of mass. Now, the center of mass has to do, or has a lot of relevance in the idea of equilibrium. In general, you can say that an object's always going to be in equilibrium, or it's going to be stable if the center of mass is above its base. So if you can think of a triangle and you have a wide base, and you have the center of mass, and the center of mass is going to be on top of that, then you're going to have a stable system. But if you have the same triangle, but you flip it, and then the vertex, the tip is on the ground, then the base is very, very, very narrow. So any motion on the center of gravity is going to tip that triangle. In the case of the human body, we can change that center of gravity by moving our extremities. We can, and by bending our body, we can change our center of gravity. Now, I'm gonna ask you guys to do a little experiment with me, and Samantha and Dylan, you need to do it too. So turn on your camera. I want to see you doing it. So I want you everybody to stand up. It's okay. So, social distance. So stand up, stand on your shoulder wide, width, or shoulder wide. And this is a very stable position for us. Your center of gravity is going to be somewhere around your belly button, so you can be in this position and be very comfortable. There's very little motion on your bodies right now. Some of you may be swinging a little bit, but most of you stand still, and you can be in this position for a long time. Now, if you put your feet together, now you can feel that your body is going to be moving a little bit. Those of you that are athletes or that dancers or that cheerleading, yeah, especially ballet dancers, this is nothing. Like they can be here, no problem. Now, if you put just one toe, one foot, you
No, I used to do gymnastics.
gymnastics. So you can see, like she is not moving at all. And on the other hand, this is very uncomfortable for me. Cheerleader, athlete,
Basketball.
which one?
Basketball.
Basketball. Now, if you do it on your toes, on the tippy toe, now it's a little bit more difficult. The what?
So I'm so sorry, I can't even do that.
And what you do to keep balance and be able to keep it on your on the equilibrium is that you move your arms and you move your leg. And what you're trying to do with that is just moving your center of gravity from your belly button, that now is away from your toe. You try to move it on top of your toe. Okay? And when you put, and when you are able to do that, that's when you find equilibrium, and that's when your body's going to be so stable. But your base is so small that it's very easy to be away from that base. Now, this is an extreme case, but you can see even if he's moving, he's keeping more or less a stable position. He's not tipping. He's controlling that his body. Yeah. Now, what we need to find out is, well, where is the center of mass of that person? Now, the way you calculate the center of mass in the human body or in a complex object like this is that you divide the body different segments. So you will have a body, you can imagine that the center of mass of the head is going to be somewhere in the center. You calculate that the center of mass of the arm is also going to be somewhere around the elbow, maybe a little bit above the elbow. The center of mass of the legs, again, is going to be somewhere above the knee, closer to your quads, just because they have more mass. The center of mass of your torso, again, is going to be somewhere maybe above the belly button. So you treat all these as 1, 2, 3, 4 different masses. Well, 6, 7, depending on the 2 arms and 2 legs. And then you do that equation that we talked about last time, like the x1, m1 plus x2, m2, x3, blah, blah, blah. You do that and you do that in 2 axes. And then you find the center of mass of the whole object. And as you move the legs, and as you move the arms, you do these calculations over and over again. And that way you can see where the center of mass is. Now, oh, get out of there. Now, this is how it looks like. So there are different ways that you can try to do this in real life. Obviously, trying to calculate the center of masses of something like this is very complicated. I mean, it's not something that you can ask a person to hold that position. You can do it with video, and then you can put markers on the person, depending on the position that or the activity that that person is doing. And you can do this for swimmers, and you can do this for gymnastics. You can do this for dancers. This is where I was talking about. So these red dots, these are the different center of mass for each individual section. So this is for the head, this is for the forearm, the forearm, the arm, the legs, and this is the center of mass of the torso. And when you calculate all of them, this is the center of mass of the person at that position. This is the base. The arms on the floor are the base. And these red lines, these dotted red lines, that's the width of the base. So as long as this center of mass is within these red dots, these red lines, the object is stable. Okay, so see, look at how it changes as the position of the guide changes. Okay, so the person is moving the legs forward, and as a consequence, the center of mass is moving forward too. So now, instead of being close to the back, it's going to be closer to the chest, well, the stomach. And notice that even though there's some sections that are outside the base, like in this case, the arms, as long as this center of mass of the whole body is above the base, the system is going to be in equilibrium. So again, you can see how that center of mass just moves back and forth depending on the position of the legs and the arms. The legs, because they have a large mass, you can control a lot about your center of mass just by moving your legs and your arms. Now, in this case, this thing is interrupting, but you can see that the center of mass is actually outside the body. It's no longer on the chest, it's no longer on the stomach. The center of mass is outside the body. And again, it's because of this bending of the body. Yeah? Makes sense? It's cool, right? Samantha, Dylan, sorry, Murs, Dylan, were you able to see that? Okay. So what we're going to try to do is, again, we're going to be talking about equilibrium. We're going to try to talk about equilibrium, but now we're going to have to modify a little bit the equation that we've been talking about a couple of weeks ago, because now we need to work with an extended object, and we need to look at the position of the object with respect to its base, and we need to look for any possible rotation. Okay. Okay, so now we're going to be dealing with cases of static equilibrium. And so far, when we talk about static equilibrium, we were talking about, oops. With static equilibrium, we were talking about one main condition, that it was basically that the net force has to be equal to zero. And we talk about that as the main condition for static equilibrium. Because forces can be decomposed in X and Y components, then we divided this as the sum of forces in X equals to zero, and the sum of forces in Y equals to zero. Now we're gonna add a new condition, and that's basically is that the sum of torques have to be equal to zero. Okay, so the first two conditions guarantee that the object is not, there's no displacement, or is displacement at a constant velocity. But right now, because we're talking about a static equilibrium, we're going to assume that there's no displacement. And the last one is basically involves no rotations. Okay. Now, we're gonna do a very quick example. Again, at the beginning, I'm just gonna do examples involving bars and just pivot point supports, boxes and stuff. And then we're gonna try to modify these to calculate the torques at different joints in the human body. Look at the equilibriums at that. So just bear with me. So I'm gonna assume that I have a plank is a long piece of wood, and I'm gonna say that this has a length of 2 meters. And I'm gonna say that this has a mass of 5 kilograms. Okay, I'm gonna put a workhorse, just a support, one here, and then another one over here. And this distance is gonna be 0.5 meters. Okay, so really quick on that drawing, identify the forces. Yeah, identify all the forces that you on that piece of wood. Identify the forces on the wood. Yeah. How many forces you found?
I have 3.
3, which are?
Well, the weight,
We have the weight.
or the center of gravity weight that goes.
So you can imagine that there's this plank as a mass is going to have a weight, and this weight is going to be somewhere. Well, it's going to be at the center of the plank. So here we're going to have the weight. Okay, and what other 2?
I have the mass of the wood.
That would be the weight.
Oh, God. Yeah, I'm not really sure.
Okay, so we have this force, okay? We're assuming that this is an equilibrium. So if we only had this force, then the wood will be falling down. So there has to be forces that oppose this weight to keep the wood in place. So we're gonna have 2 extra forces, and those are gonna be normal forces. And there's gonna be a normal force here. And then we're gonna have a normal force over here. So I'm gonna call this normal force 1, and this is gonna be normal force 2. Okay, now what I want to find out is what are the magnitudes of this normal force. I want to find out what is normal force 1 and what is normal force 2. Okay, now if I do a free body diagram, the way we've been doing it before, I'm gonna have an X, I'm gonna have my Y, and then your free body diagram is gonna look something like this. It's gonna have your weight going down, and then you're gonna have your two normal forces pulling up. If you are trying to do, okay, this is an equilibrium problem, I'm gonna try to solve for those forces. I don't have forces in X, just there's no forces in X. So the only equation that I can write is that the sum of the forces, the sum of the normal forces minus the weight is gonna be equals to 0. And we have two unknowns and one equation. So there's no way you can solve this problem just by using this free body diagram. Okay, so the way we can try to solve this is by using the third condition. Okay, this plank is not only static, it's not, well, it's static, it's not only being not being displaced, but it's also not rotating. So we can add a third condition and say, okay, all the torques have to be equal to 0. So now what we are trying to do is, okay, we can try to calculate that torque. Now, what do we need to calculate the torque? Yeah.
Gravity, mass, so R equals perpendicular.
Okay, what will be the value of R? So that was a tricky question. So in order to calculate the torque, you need to define a pivot point. Again, most of the times, like if you are trying to calculate the torque on a shoulder, or you're trying to calculate the torque on an elbow, the pivot point is obvious, it's given by just the geometry of the object. You know that the shoulder is going to be your pivot point, the elbow is going to be the pivot point. But in this example over here, we really don't have a pivot point. These are being supported. So technically, I can pick any pivot point that I want. Okay, I can put it anywhere I want. I can put it somewhere around here, or I can put it here, or I can put it here, or I can put it over here. Okay. A technique to try to solve these problems is to put the pivot point, or to put the origin of your system in one of the forces that you don't know. You don't put it on the weight because you know the weight. So you put the force either, you put the pivot point either at the normal force number 1 or normal force number 2. So I'm going to put it normal force number 1, just so you get it, you see what's going on. So this is going to be my pivot point. Okay. And now I'm going to have two forces. The force of gravity pulling down, and I'm going to have the normal force pulling up, and here I have the other normal force. Okay. Now I'm going to calculate the torques. So the sum of the torques is going to be the torque caused by normal force number 1 plus the torque created by the weight plus the torque created by 2. Okay? And I know that the torque is going to be the distance between the pivot point and the force. So what will be that distance in the case of torque number 1? Jacob? The distance between the pivot point and the normal force 1. This one. So this is my pivot point, and my force is just right there. So R is going to be 0. There's no R, there's no distance. So this torque is 0. Yeah, Jacob? Okay. So the first one is going to be 0. The second torque is rotating counterclockwise, so it's going to be negative. And the force is going to be, sorry, the distance is going to be 1 meter, sorry. It's going to be 1 meter. And the force is going to be mass times gravity. And the angle is 90 degrees, so the sine of phi is going to be sine of 90 degrees. That's going to be 1, so it's just going to be that. And then force number two, the torque for force number 2, or the force for normal force number 2, that's going to be positive. That's going to rotate in counterclockwise. And we're going to have the magnitude of that force that I don't know what it is. And the distance is going to be 1.5 meters. Again, sine of 90 degrees. And these have to be equal to 0. So now I have one equation, one unknown. So I can solve that one. Okay, and then I can do it really quick. And I get a force of 32.67 newtons. Okay, now that I have this force, I can come back to my original equation over here and find for normal force number 1. Yes?
The equation that you just did, yeah, where did that come from?
Where did this one come from?
Yeah.
This is the sum of torques. This is the condition equilibrium when the torques have to be equal to 0. So this part over here, this is the torque created by the weight. And this one over here is the torque created by this force. Yeah. So from here, you can find that the normal force number 1, that's going to be equals to now. Yeah. It's going to be 16.34 newtons. Yeah, makes sense? Ish. Okay. Try to do this on your own, very similar. Okay, so this is a springboard. And I'm going to assume that the mass of the springboard, this is 30 kilograms. It has a length of 3 meters. And this second support is at 1.5 meters. And the diver has a mass of 60 kilograms. Okay, and you can imagine that this springboard is attached here on the first hinge. Is just bolted or something. It's just allow it to rotate, and here it's just standing. It's just leaning on it. And what I want to find out is what is the force on these supports. Okay, so give it a try. Hey, you've fallen asleep.
Yep.
have two masses. So the mass of both mass is the one. But the mass of the for the person is not here. But the mass of the ball is. So you have two masses. So you have two weights. One for the of the person, one for the ball. So if you're missing one torque, you're gonna have one torque per force. So you're gonna have a force of the weight because of the board. You have a torque because of the person and two torque because of this. Okay. So you have two masses. So it's gonna be you have two masses. You have the board and the person. You have the weight of the person and the weight.
Okay, so I'm gonna do it really quick. I think most of you either move really fast or they're stuck in some very basic stuff. So what I'm gonna do is I'm gonna set a frame of reference and I'm gonna place my origin. I'm gonna place my pivot point here, the first support, just for convenience. Uh, I'm gonna have different forces. I'm gonna have a force here. Oops. So I have a normal force here. I'm gonna have the weight of the springboard, and the weight is gonna be somewhere here at the middle. So I'm gonna have a weight of the springboard. I'm gonna have a second normal force here, and I'm gonna have the weight of the person pulling down. So I'm gonna have a weight there. The free body diagram, I think this is what everybody got correct. I think most of you. No, oh, this the free body diagram gonna look something like this. You have two forces, normal force pulling up. Yes.
So is the weight one or the weight two, the weight of the person?
The weight two is gonna be the weight of the person, and the weight one is gonna be
Weight of the board.
the weight of the boat. And here I'm gonna have the two weights. Okay. Again, we don't have any forces in X direction, so if we just do a free body diagram, we cannot solve it. We will have two unknowns, so we need to use torque. So I'm gonna place the torque, the pivot point of my to calculate my torque, I'm going to put it on one of these normal forces. I'm going to pick N1. So my diagram, or my free body diagram, is going to look something like this. So when you are working with torque, the free body diagram looks a little bit different. You are working with an extended object. So I'm going to have a force here. I'm going to have another force here, the weight, and the second force here, the second weight there. And this is going to be, this distance is going to be 1.5 meters, and this distance is going to be 3 meters. Okay, so from this, I'm going to have two equations. From the first free body diagram, I'm going to have the sum of all the forces is going to be equal to 0. I'm going to have that. And from the torque, and again, we have two unknowns, one equation. There's nothing we can do. And for the second equation for the torques, I'm going to have the torque caused by force number 1 plus the torque caused by force number 2 plus the torque of weight 1 plus the torque of weight 2 has to be equal to 0. Okay, the first torque is going to be 0 because we don't have any distance between the pivot point and that force. So this is going to be 0. And then I can start solving. So I'm going to have the normal force times 1.5 meters. And that's going to be negative. No, sorry, that's going to be positive. And these are going to be negative minus M1G times 1.5 minus M2G times 3.0. It's going to be equal to 0. Okay, and then I can say, okay, the normal force is going to be for example 130. 30 times 9.8 times 1.5 plus 60 times 9.8 times 3.0 over 1.5. You can simplify it a little bit. And you can simplify it even one more step. Yeah. So I have 1,470 newtons. Yeah. Yeah, everybody got that? Yeah. Jacob, you got it? Okay. Any questions? Rich? Okay. Now we can calculate where the center of mass is. So having the mass of the person over here and having this support, or sorry, the mass of the person and having the mass of the board, I can calculate the location of the center of mass of both of them. So the location of the center of mass will be x1 m1 plus x2 m2 divided by m1 plus m2. Now x1 is going to be the location of the center of mass of the board, which is going to be 1.5 meters. M1 is the mass of the board, that's 30. And the location of mass of the person is going to be at the location of the person. So this is going to be 3 meters, and this is going to be 60, and divided by 30 times plus 60. And that's going to be 2.35. Okay, 2.35 meters from my origin, which is the pivot point. So that means that the center of mass is going to be 2.3 meters. So it's going to be somewhere around here. Yeah. So if we didn't have that support on the back, this will flip and it will fall. Like this center of mass is outside the base, so it will flip. Okay. Make sense? Okay. Again, very similar problem. Okay, we have a board, and this board has a mass of 6 kilograms. And the length of the base in this case is going to be 30 centimeters. Okay. This board has a length of 50 centimeters. Okay. So in this case, Trinity, where is the center of mass of the board?
Would it be in between,
In between here? Nathan?
It would be in between them, it's just not perfectly between them, it's at 25 centimeters.
It will be at the middle, halfway the length of the board. So if this is 50 centimeters, the center of mass is going to be at 0.25 meters, at 25 centimeters. So it's going to be probably somewhere around here. Yeah, Trinity? Actually, so remember, if you have just regular shapes, the center of mass is always going to be at the geometric center of the figure. So if this is 50 centimeters, this is going to be 25. Yeah, makes sense, Trinity? Okay, so it's going to be there. So this structure, the way it is going to be stable. It's going to be supported. We can calculate the forces on each one of the supports, the way we have done it. So, but we know that that thing is going to be in equilibrium because the center of mass of the board is in between or is above the base of the structure. Okay. Now, I'm going to add a box, and this box is going to have a mass of 3 kilograms. Okay. Now, this mass for this box is going to have its own weight. It's going to have its own center of gravity. And when we calculate the center of gravity of the box and the board, the center of gravity is going to be pushed towards the right. It's going to be displaced this way. And the more I move this box to the edge, the center of gravity is going to keep moving farther and farther to the right.
What point does it tip past?
So we want to find out how far can I move this box before the whole board tip. Okay? Make sense? So how do you do this kind of problem? So how can you solve this? Well, basically with calculating the location of the center of gravity. So I'm going to assume my frame of reference that's going to be here. Okay, so all my distances are going to be measured by here. And I'm going to try to calculate the center of gravity of the two masses to be 30 centimeters. This is the limit of the location of the center of gravity. If the center of gravity is bigger than 30 centimeters, means that it's outside the base, so it's going to start tipping. Okay? So I'm going to solve for this. So the center of gravity is x1, m1 plus x2, m2, m1 plus m2. What mass did I say for the box?
3.
Thank you. Okay, so I know x1. x1 is the location of the center of gravity of mass 1 or the board. So I know m1, x1. So x1 is going to be 25 centimeters. And m1 is the mass of the board. So this is going to be 6 kilograms. x2 is what I want to find out. And I know that m2 is going to be 3 kilograms. And I know that the center of gravity, the one that I want, the center of gravity that I need, has to be 30 centimeters. Anything bigger than that, the box tilts. Okay? Oh yeah, so now I can solve for, I'm going to try to solve for x2. So here just going to be a bunch of algebra. So I'm going to multiply quantity m1 plus m2 on both sides. So I'm going to have okay, I'm going to subtract x1 m1. And then I'm just going to divide by m2. Oops. Okay, and from here you can just substitute the values that we got and get so I'm just going to write it down. So I'm going to have you got that? Oh, no. True. Yeah. Jacob, you got that? Oh, no. This is 3.
That would be why I didn't twice that now.
Yeah, I'm not getting that.
Okay. Forty centimeters. Okay, that makes sense. Okay, so that means that you cannot move that box 40 centimeters away from the first support, or the whole thing's gonna tilt. Okay? Make sense? Ish? Quack? Okay. Any questions? No? Okay, so that will be it. See you guys on Monday, or Friday.
I actually have a question from Monday's class.
Sure.
So I was like reading my notes last night and I was confused. When we're talking about R, we're talking about what?
The distance between the pivot point and the mass. Or,
Okay.
or the pivot point and whatever the force is.
Okay, so that would be like these lines, right?
Yeah.
Okay. So then if we like go down here, R would be like the distance between M1 and your center of gravity,
Correct.
right? Okay. Okay, then
And the pivot point.
right. Okay.
Yeah. So in this case, is the distance between M1 and your pivot point.
Mm-hmm. So when we get down here, it ended up being like, I don't even know. We never actually solved for this.
Yeah.
Well, yeah, but we didn't do it with like numbers. So like the equation for this was just T1 plus
Oh, yeah.
T2 equals 0. But then I'm confused, like how did we get this from like our original torque equation?
So there are two equations. So
Yeah, there's like the torque RF,
yeah, it's
and
like
then there's like the sine one.
it's like saying, okay, force equals M1, first time acceleration, and then having the sum of forces equals to 0, and then you have F1 plus F2 equals to 0.
Mm-hmm.
So
They're completely different. I mean, like this one's solving for force, and this one's
so it's the same. You have torque equals R F sine of phi.
Yep.
That's the equivalent.
okay.
And then you have torque 1 plus torque 2 equals to 0.
Okay.
Okay. So this equation is the
Mhm.
equivalent of your F equals ma.
Okay.
And this equation is the equivalent of F1 plus F2 equals 0.
Got it.
Yeah.
Can I have that piece of paper from you? So I
Yeah.
can Click on it. Perfect. Thank you. That makes a lot more sense. I was like confused as to like what equation